So the first two are removable discontinuities. That's where the discontinuity is in line with the function. So we have the point right there. So if we were to make the value of that point equal to that equation, it would be continuous at that point. We can make a piecewise function to make it continuous. If this value right there wasn't there but here, that also would be a removable discontinuity. So those two types of our discontinuities are removable because we could make a piecewise function to remove them. This is an infinite discontinuity where the function goes to infinity. This one is not removable. And then when we have what's known as a jump discontinuity, again, not removable. And you might have seen these as a piecewise function, but actually that function can be written without a piecewise function. So this equation is actually written like this. That stands for, that actually what it does is it basically takes any number and truncates it to the whole number. It's used quite a bit in computer science and programming. You're not going to see it very often, but it's definitely used in computer programming and stuff like that. So if you're going into that field, you might see those. All right. Let's look at some graphs. So here's a function, here's a graph. So that what numbers in the interval from -4 to 4 is G discontinuous? So where are the discontinuities in this graph? Where's one of them? No, because it's got the bracket, so it doesn't actually go to that point. So yeah, you're fine there. So there isn't actually another one. What type of discontinuity is -3? Yes, that one's removed. Alex doesn't ask you this, but it's nice to know. What kind of discontinuity is at 1? That's a jump. Okay. Where's one of the discontinuities in this one? -2. What kind? That's the jump. Is there another one? At 1. What kind of discontinuity is that? That's it. I think the graphing ones are pretty easy. Pretty easy to see. So I do many more of those. Let's do the next set. So one of the things that you probably did in pre-calculus, and you didn't know why, and it probably was a bit of a pain in the butt, was composite functions. So while composite functions don't seem to be very important, they become very important in calculus. Because what it allows us to do is to break apart the function and solve pieces of it in a different way. So this is another one of those topics where you're probably not going to do it a bunch as a limits, but it's a really good practice and a way to understand composite functions in a different format. So we're looking for the limit as x goes to -4 of -2f of g of x. And they give me that g of x is this. So what we need to do first, we work from the inside out. We need to, because of the way this is set up, I actually can find the of the limit as x goes to -4 of g of x. I can put the limit on the inside. Actually, I can put a limit on the outside of this one too. Of f of x. So let's find the limit of g of x as x goes to -4. How do I do that? Plug in -4. If I plug in -4, I get 1. Yeah. Oh, actually, that was the value of that, so I don't need the limit up there. So now I have f of 1, which we know is 3. Correct? Because that's what they tell us up here. So this one's got one little side benefit because of the way they're doing this problem. If for some reason you get a number that is not -15, -4, or 1, you know you screwed up because you can't go any further. So the f of g of x is 3. So my final answer is -6. So yes, there's a lot of little places that you can screw this up. All right, so let's look at this one. So we're going to start on the inside. So I'm looking for the limit as x goes to 5 of 8x over x minus 5. So what does that equal? So this becomes 8 over 0, right? Not 8 over 0, actually. 40 over 0. So since they don't both come out to be zeros, probably not going to be able to factor anything out of this problem. To at least get rid of the x minus 5. So this doesn't exist. Since that limit doesn't exist, the entire limit doesn't exist. So the answer is does not exist. That is a possible outcome. So if the limit of the interior function doesn't exist, I can't do anything about the outside. It automatically does not exist. Let's do this one. All right, one more of these. All right, your turn. Try this one. So what's the limit as x goes to negative 2 of g of x? Everybody understand we got the 14? Okay. So now I just have f of 14 minus 3. F of 14 is 2, so 2 minus 3 is a negative 3. That answers your question earlier about this topic. That's the topic you asked me about. So it's one of those topics that looks really complicated, but once you see it, it's really actually not too bad. Next one's a little more complicated. All right. It tells you the function has a removable discontinuity. So, but how does it know it has a removable discontinuity? So step one is let's figure out where that discontinuity is, and then we will determine if it is removable or not. So where is the discontinuity in this problem? It is going to be at A, but what value is A? Why? Yeah, so your discontinuities are going to be where the domain restrictions are. It's where things don't exist. So where does this problem not exist? At x equals negative 3. Because that's going to make it a 0 on the bottom. So A in this case is -3 because that's going to be where my discontinuity is. And in this case, I only have one of them. So when we're looking at the limit as x goes to -3 of 4x plus 12 over x plus 3, you end up getting 0 over 0 when you plug it in directly. So we have, when it becomes that 0 over 0, there's a very good possibility that it's going to be removable. So what is that limit? Because that's going to be the b. Because we want to know where it's actually going to at that point. So how can we simplify this problem down to figure out where that graph actually goes to? Yeah, the bottom I really can't do much to. It's a linear equation. The top is also a linear equation, but there's more numbers there, so let's see what we can do. We can pull out a 4 out of the top, and I'm left with x plus 3, and I'm left with x plus 3 on the bottom. So I cancel those out, and this equals 4. So the value that I would want for b is 4. You can verify this by looking at the graph. If we look at the graph, this is the graph. And we were going to 3. Oh, -3. And while -3 doesn't exist, I could easily add a number in there to fill in that point, and now it's continuous. That makes sense? Let's do another one. Yeah.
Would that be considered piecewise because it's two separate functions?
Yeah, so now when we're looking at this right here, that would be a piecewise function. But it's still a function. And it's still a continuous function. So you have piecewise functions can be non-continuous. That's actually one of the ways you can get those crazy discontinuous graphs is with the piecewise function. However, piecewise functions like the one we have here, this is a completely continuous graph. There is no more discontinuities, there's no more breaks. Because we filled in the discontinuity with a value specifically for that point to make it continuous. All right. Look at this one. So where is my discontinuity? Yeah. So if we're looking at it again, we're looking at in essence, domain restrictions. So I would look at 3x plus 1 equals 0, because that would make it not work. So x equals negative 1/3. So A is negative 1/3. All right, so if we're saying that's a removal of discontinuity, I need to be able to simplify this problem down to finds. So now I got to find the limit as x goes to negative 1/3 of 3x squared plus 16x plus 5 over 3x plus 1. So how do you want to do it? Yeah. Any ideas?
Factor by grouping.
Could factor by grouping on this one. Well, we could factor. We have to make it by grouping because we only have 3 pieces right now. We need the 4 to be able to do the actual grouping method. So yeah, but we can split this to make it so that we can do it by grouping. All right. So we're looking for 2 numbers that multiply to 15. Because if you're going to do it by grouping, you're looking at the 3 times the 5 and add to 16. So multiply to 15 and add to 16. This one's pretty easy. 15 and 1. I'm going to show you another way to do this in a minute. So we can pull out the 3 and an x on this side, and I'm left with x plus 5. I pull out the 1 on this side, I'm left with x plus 5. It's 1, x plus 5. So that means this, the 3x plus 1s will cancel out. That means that is x plus 5. So if we plug the 1/3 into that problem, I would get what? I would get, yeah, 4 2/3. So 14/3. And there's a very important line right here. It doesn't want it as a decimal. So you can't just go to decimals and get the thing because it'll give it to you as a decimal. Or the Alex graphing calculator, you'll get it as a decimal. So you want an exact value, so you need to actually do the calculation. The other way you could have done this, since we have that negative 1/3, you actually could have done synthetic division. And you'd been left with 3x plus 15, which if you multiply by the 1/3, or x, if you took out the 3, you get the x plus 5 is left over. So they all work. Just depends on what method you find better or easier to work with. Do another one of these.
Actually, the
Which one?
actually over kit 14.
5 minus 1/3. Because we plugged in the 1/3 back into the X. Because that's what my limit was going to. So 5 would be 15/3 minus 1/3 is 14/3. All right, try this one. I also try when I'm going through and doing these because it randomly picks problems. So you're going to get a variety of difficulties. I have it more granular. I can pick the more complicated ones. So I try to do easy ones to begin with and do the harder ones. So you see both shapes. So you're not going to be totally surprised by a problem that shows up in Alex. How do you want to simplify this limit? What do you notice about the top? I can factor out 5. I can actually factor out more than that. I can factor out a 5 and an X. The 5 is really going to be helpful. The X is actually even more helpful because then it gets me down to my X squared. Because then this actually becomes pretty easy to factor. I get X minus 5 and X plus 1. So this ends up being 5X, X plus 1. So if you plug 5 into that, you get 150. So big numbers can happen. All right, let's look at another different type of problem with discontinuity. You won't see that part. So this problem gives you a piecewise function, gives you the x. And what it wants is it wants you to take the ability so that it is continuous for all real numbers, so that there is no discontinuities. Okay? So, for there to be no discontinuity, the place at the where the piecewise meets has to be the exact same value in both functions. And there cannot be any other discontinuities in the function. Okay? So, my suggestion to save yourself work would be to look and see if there's any other discontinuities possible before you do the actual all the work to find K. Because in a problem like the one that I have on the board now, where is there a discontinuity? Where does this problem not work? At 0. So this problem right here x cannot equal 0. Is that within that domain? Yes. So there is a discontinuity at 0 that I would not be removing by doing this work. So there is no value that I could make K to remove all the discontinuities. I can remove the one at 2, but I can't remove the one at 0. Okay? Does that make sense or no? So if we looked at this problem on a graph, and so here's the graph. This is what this graph looks like. I can change this number to whatever I want, but there. So like right now it's there. There's a discontinuity at 2, and there's a discontinuity at 0, right? If I make this negative 1/2, I've eliminated this discontinuity at 2, right? It's now a connected dot, but I did not remove the discontinuity at 0. Okay, so there is no way to make this problem continuous the way that it is written. Does that make sense? Or no? Yes, no. Maybe so. All right. If this was reversed and it was like that, I could. Because that 0 is no longer in my original domain. All right, that 0 no longer exists. That possible discontinuity doesn't exist. And then I can do the problem. So it's important to look at not only this, but the original problem as well, and see if there is any other errors that possibly could show up or discontinuities that could show up. And I would do that first before you do all the work. Because otherwise, you're going to do all the work and then find out the answer was no. All right. Obviously, that group of problems is always that. Let me find the next group of problems. All right, let's look at this one. Step one, look to see if there's any other discontinuities that could cause me a problem. So, is there any discontinuities in either in the first function or the second function? What was it? 4. So 4 does not work up here, right? So x cannot equal 4. Is that within the domain that they gave me? No. Okay, so we can do this problem. Okay. For a problem to be continuous, the limits have to be the exact same. So the limit as I get to 3 needs to be equal to the actual value. So if I look at the limit as x goes to 3 from the left, and I look at the limit as x goes to 3 from the right, we can find those two values. So what is the limit as x goes to 3 from the left? So which one am I looking at? The top equation or the bottom equation? The top equation. Okay, so if I plugged in 3 to that, what do I get?
1. Right, this side.
Yeah, because the bottom's 1, so that becomes 2. And then from the right, I'm going to use the 3x plus k. If I plug 3 into that, what do I get? 9 plus k. Yes, you're going to have a k. That's okay. That's actually very important for this problem. All right. Does everybody understand where I got the 2? Okay. Does everybody understand where I got the 9 plus k? For this to be continuous, those have to be equal. So I would set 9 plus k equals 2. So k has to be -7. All right. If you want to verify this to make sure that it works, you can use Desmos for that. To do a piecewise function on Desmos, you write it like this. You write your function, and you put those little curly brackets around what the domain is. So the first one was x is less than 3. Don't worry about the equals. The equals is not going to matter, but you can put the equals there if you want. It doesn't really make a difference. So x is less than 3, and x is greater than or equal to 3. And then when you look, I should have one continuous line. If I don't, then you might have messed up. So you can use Desmos to verify your answer before you put it into Alex to get it right. Okay? And it's all about that little box there. I will actually put in the notes So you can see that down the line and remember what it was for. I got the sign of the wrong one, but that's fine. Let's do another one of those. All right, try this one. All right, what's step one?
Check for discount.
Check for discontinuities. Do I have any discontinuities in this problem? At 0, is 0 within the domain of this problem? Yes. The first one is x is less than or equal to 4. 0 is in that domain. The answer is no. Always check that first. Save yourself work. And if you get lucky, you'll get 3 of those, and you don't have to do any work for this. All right, this one you actually have to find the K. So you take, once you realize you can do it, find the limit of both directions, set them equal to each other, find out K's. All right. Very important theorem. The intermediate value theorem. So, the intermediate value theorem states that as long as f is continuous on such a domain, then there is a number between f of a and f of b where they don't equal each other to begin with, so they can't start the same thing. There's some number c in between that would equal that value. So here would be a very easy example. Driving down the highway, you're averaging 65 miles an hour. Okay? The cop pulls you over when you're doing 55 and tells you that you've been speeding. How does the cop know you're speeding? Nope. You've been averaging 65 miles an hour, but when the cop pulls you over, you were doing 55. How does the cop know you're speeding? Because at some point, you had to be doing greater than 65 miles an hour, right? Otherwise, the average wouldn't have worked out to be 65 if you're going slower now. The intermediate value theorem basically states that if I'm on both sides, to get from here to here, I have to cross everything in between. Okay? So if here was 55, and here was 80, somewhere in the middle is 65. True? Totally makes sense when you say it. Like, yep, between 55 and 80, so 65 has to exist. As long as f is continuous, that is what this problem states. So somewhere between those two values, there exists a value of 65. The place that this is used most often is finding zeros. If I'm below zero at one point and I'm above zero at another point, at some point between it, it has to cross zero. So that means there has to be an actual answer or a zero term between those two values. Now, this time I'm actually going to use the Alex problem to show you because it's long. And there's lots of boxes to check. So this is the Alex problem. I will copy and paste this into the notes too, so you'll have it there, but it'll be in the video. Considering the following equation, 2x to the third minus 15x squared plus 14 equals 0. Is that function continuous? So how do you know it's continuous? What kind of function is that? It's a polynomial. Polynomials, by definition, are always continuous. When we're thinking about continuity, we're really looking at domain restrictions. Okay, those are in essence the exact same thing. So is there a place where this value does not exist? No, it's a polynomial. It exists everywhere. All right, it doesn't fall into the dividing by zero. It doesn't fall into the square root problems. It doesn't fall into the log problems. It's continuous everywhere. So why is it continuous? Well, it's continuous because it is a polynomial. What's a rational function? That's the one we have division. Rational functions mean fractions. So a rational function would be continuous everywhere except for where the denominator is 0. If that is not within the domain that they're looking at or that interval that they're looking at, you're fine. We can continue doing the problem. It's going to be continuous. So that's where it says is continuous on that because it's a rational function. It's not in there, we're good. Or it's not continuous because it does fall into there. This problem, it's a polynomial function. We've got the first answer. The second part of so that's the first step of the intermediate value theorem, is that we need to make sure it is continuous on that interval. The second part is we need to make sure that the values do not equal each other. Okay? So you're going to plug in -1 to the problem and 9 to the problem. So you plug in -1 and I'll plug in 9. Got -3? If you're using the Alex calculator, there's a nice little trick. Once you get the answer, if you hit undo, it goes back to where you had the problem. You can then just change those two numbers there to a 9. You don't have to retype the whole problem. All right. Are they equal to each other? No, they're not equal. Okay. That's step 2 of the intermediate value theorem. The endpoints cannot be equal. If they are, we're done. Okay, so it's continuous. They're not equal to each other. Good. Now, are they on either side of the value that I'm looking for? So in this case, we're looking at 0. So is f of -1 greater than 0, less than 0, or equal to 0? It's less. F of 9, is it greater than 0, equal to 0, or less than 0? Greater. So we're good. So, is this function continuous? Are they equal to, or are they not equal to each other? The endpoints?
Yes.
Yes. Are they on either side of the value that I'm looking for? Yes. So, as long as you can say yes to all these 3 questions, yes, we can apply the intermediate value theorem to state there is some value between -1 and 9 where the answer is 0. I don't know exactly where. I'm going to guess it's probably pretty close to -1 because it's closer to 0, but it is somewhere in between. I'm copying it to the notes, and then I'll hit yes. So this way you have it in the notes. Yay, I got it right. How about that? Just like you guys, there's times where I click and go, did I get all that right? All right, let's do problem type 3. Eh. There we go. All right. Is this function continuous or not continuous? Why?
Because it's a rational function, but where f is defined is outside of the domain.
Yeah. So where is it not defined? At 4. So it can't equal 4, right? But I'm only looking from 0 to 2. So I'm good. So it's that one. All right. Plug in 0 and 2 to the problem. Again, it wants the exact values, not decimals. So make sure to write them as fractions. All right. Are they equal or not equal? Not equal. F of 0, less than, greater than, or equal to. F of 2, less than, greater than, or equal to. What is it? Less than. All right. So can we apply the intermediate value theorem? Yes. They're not equal to. It is continuous, and one is greater than and one is less than. And either value would give me 0. Let's see. Trying to find one that doesn't work. And I'm not having luck. Really? There we go. Okay. All right. Let's look at this one. What's the it says it's continuous. It's not continuous. So what is the value where it's not continuous? X equals 2. What is the interval that I'm looking at? 1 to 5. 2 is within that. So therefore it is not continuous. Doesn't mean you can't do the rest, you don't have to do the rest of the problem. So plug in the 11, plug in the -1. They're not equal, or plug in the 1, plug in the 5, you get 11 and -1. They're not equal to each other. They are on either sides of them. However, because it is not continuous, we cannot do the intermediate value there. Because that means there is a value between 1 and 5 that doesn't exist. So therefore, I don't know what else might not exist. Okay? So you still have to do it all, but that first one right there basically forces it to be a no. If any of these don't work, like, so if that's not continuous, if this is equal to, it won't work. If these are both the same direction, it doesn't work. So it's got to be continuous, not equal to, and both directions here for it to be correct. All right. Let's do the thing that everybody in here I know loves. I'm sure this is your absolute favorite topic in the world. Everybody loves trig, right? I'm being sarcastic, I know. How many had Mulkenstein for pre-calculus? What's the one thing she made you do for trig?
No, I absolutely.
She made you memorize the unit circle. She wouldn't let you use one. You had to know it. There's a reason for that, because it's extremely important when you're doing the trig problems. So, this is the unit circle. That's not the one I want. That's the one I want. This is the unit circle. I would highly suggest you don't need to memorize it, but you do definitely need to be able to find it quickly, and you should know certain values from it. Okay, so the biggest and most important ones, if you notice, is that they kind of repeat themselves. The numbers around the outside kind of repeat themselves. First, your y is sine, your x is cosine. Okay, y is sine, x is cosine. So if you're looking at this, sine goes at 0 goes from 0 to 1 to -1 to from 0 to 1 to 0, go away, to -1, and then back to 0. Right? Up, down, up, down, up. For you. Yeah. Pi over 6, pi over 4, pi over 3. The pi over 4s are always the square root of 2 over 2s, no matter which quadrant they are in. It just depends on your signs. So if you're in quadrant 1, everything's positive. If you're in quadrant 2, your x is negative, your y is positive. Quadrant 3, your x and y are both negative. So think back to your algebra when you're doing those. That's going to help you with this. Your pi over 6s, again, are all the pi's with 6s are the same. Pi over 3s, they're all the same, just different numbers. So if you can remember the beginning, like this first quadrant, you can use what you know about the quadrants to find all the rest of the answers. All right. The reason that's important is because in problems like the one we're looking at right now, I need to know what the cosine of negative pi over 2 is. I need to know what the cosine of, or the sine of negative 3 pi over 2 is, to be able to plug those values in. Okay. You can use, the problem with using a calculator for this is, I'll show you. Sine of 5 pi over 6. So if, say, we were doing the sine of 5 pi over 6 in radians, that one works out pretty nice. It's a fraction that's easy to find. But 5 pi over 3 is not. Okay? And you're going to want them as exact answers, not as decimals, which means you're going to want the square roots. So that's why knowing that unit circle is going to be helpful to find. They're not going to use values that are outside of that unit circle. All the values you're going to see will be pi over 2s, pi over 3s, pi over 4s, pi over 6s. Yes. If I'm going to use it, I will give it to you. Oh, actually, I will before the classroom, ask me about tests again. I'm going to actually tell you something about tests because I totally forgot to say this the first day. Yes. Oh yeah, I'll switch back to it in a second. You're going to go backwards. You're going to go backwards. So technically, negative pi over 2 is the exact same as 3 pi over 2. One of the other things you did in pre-calc was learn about coterminal angles. That's because you just rotate around 2 pi. So these are all the things that you did in pre-calculus that are going to come back to haunt you if you did not remember them, unfortunately. You will practice them a lot. All right, so plug it. The nice thing about the 2's is they're on the ends, the halves, so they're pretty easy to work with. So I have 5 plus 3 cosine of, I'm going to use it as 3 pi over 2 because it's easier to work with. And then sine of 9 pi over 2. I'm going to go around the circle a couple of times. So if I go to my unit circle, cosine is your x value, so cosine of 3 pi over 2 is 0. So that's 3 times 0. Sine of 9 pi over 2, so that would be 4.5 pi. Yeah. So if I take away 2 pi, I can take away 2 pi twice, and you're back with pi over 2 for sine, which is 1. So this answer is 5. Remember what I said at the beginning? Your mistakes are not going to be calculus based. I know every single one of you knows how to plug in the value. I know that you've done it a bunch of times in here. That's all we're doing to this problem. The mistakes you're going to make is not remembering your trig functions. All right. 3 times 3 pi over 2. All right, let's do this one. They're actually being pretty nice. I haven't found one yet that had like pi over 6 and stuff in it. All the ones I keep finding are the halves. All right, let's plug in 3 pi over 2. All right, so my bottom is just -2. What about the top? Yeah. So what I would do is I would not cancel those out. I would not cancel that and that out. I would just do 6 pi over 2 plus 3 pi over 2, which gives me 9 pi over 2. Because if you canceled it out, the first thing you're going to have to do is put it back to put the fractions together. So sometimes that's where looking a little further ahead of like, okay, what's my next step going to be? Might save you some work by canceling stuff out when you don't need to. So sometimes it's actually better not to reduce your fractions and things like that until you're almost done with the problem. You also could have noticed that those were the same and you had 3 pi over 2. All right, so we got 9 pi over 2 divided by -2. If you want to do this out by hand, keep change flip. So I got -9 pi over 4. That's my final answer. Now, I will tell you what I've noticed going through like 15 of these problems now while I'm sitting here watching you guys work. Some of these problems look insanely complicated, like this one. Believe it or not, almost all of them break down to be very simple. So why I'm telling you that is, I don't want you to look at the problem and freak out. Just try it. They tend to break down pretty easily, like this one. This one breaks down extremely simple. Like, what's pi minus pi? 0. So that whole part in the beginning is 0. Cosine of 4 pi. What's one circle? Nope. One circle is, well, yes, the answer is 1. One circle is 2 pi, right? So I'm literally just going around twice. And I'm right back at the beginning. So cosine of 4 pi is 1. What's a half a pi plus a half a pi? Right. What's sine of pi? 0 plus pi. So the answer is -1 over pi. Okay, that's what I said. That problem, looking at the beginning, I guarantee you, you would have looked at it and go, nope. It really wasn't that bad. Okay. I looked at it and go, oh, they're going to have fun with this problem. And then I'm like, oh, that really wasn't that bad. So like that's the thing. Like they tend to make them look more complicated than they are. Almost every problem that I've found so far comes up with pi over 2. They're all those. So you really don't need to know the pi's over 6s and 4s and everything else right now. You will. We will definitely be using those, just maybe not for this topic. All right. Oh, fun. Let's do problem type 12. I don't think I can get much harder than the hardest problem type they've given me. And then I will tell you about the test that I totally forgot to tell you the first day, which will help solve some of your stress. Huh? What? The whole problem? It might be. I didn't do it yet. Let's see. Nope, it's not 0. You do get a lot of zeros in it, but the final answer is not 0. But remember, negative pi over 2 is just going backwards. So it's really the same as 3 pi over 2. So what's cosine of 3 pi over 2? 0. So that's a big 0. What's sine of 0? 0. So the bottom is negative 3 pi over 2. Now the top is cosine of negative pi. So what's cosine of pi? Is negative 1. Because it goes from 1 to 0 to negative 1. So my final answer is, so I get negative 1 over negative 3 pi over 2. So my final answer is 2 over 3 pi. Okay, your test. I told you test on paper, you get partial credit, all that other wonderful stuff. You also get an index card. So you are allowed to bring one 3x5 or 4x6 index card with anything you want on it. It has to be handwritten, and nothing can be stapled to it. Okay? So while you're going through and doing the practice test, if you have to look something up to do that practice test, write it on your index card. Okay? Yes. Nope, you can use both sides. And for the final exam, you're going to get one sheet of paper. So you got one of two options, actually. I've done both of these for the final exam. And I'm not going to change. You can use either one. You can use a whole sheet of paper, both sides for the final exam to write all your stuff on. Or you can just use your index cards. You can keep your index cards and just use your 3 index cards. Because in essence, you've wrote all your notes on the index cards anyway, so you might as well just save that and use that for the final. You can do either way. So write your index cards out nicely so you can keep them and keep them. So but yeah, when you're doing the practice test, if you need something, write on the index card. Yes. 4x6 is the biggest index card I'll allow. So that's the biggest packs you can buy, like at Staples and stuff like that. It's a 3x5 or 4x6. Yes.
Are there gonna be any like, written responses?
No. Nope. No, oh, well, no, there's not going to be any, oh, I need you to explain your answers, but I do need you to show me your work. Any other questions? Yes. Oh, absolutely. Yes.
Two questions. Only Vendos or they use them probably not use some, but like they use K84.
Oh, yeah, you can use the TI-84, yeah.
Second question, what is it probably on?
September 16th is the second chapter 2 test. No, chapter 2 test. The final exam is December 9th. You're welcome. Any other questions? Good, go home and do Alex.